Hello, welcome to this webinar, Vehicle Lightweighting, Remove Weight, Not Strength. My name's John Aldred and I'm Director of Product Management for nCode Software Products, and thanks for joining us today. So we're going to be looking at some of the issues around vehicle lightweighting. We're going to be looking at how that impacts durability and how that also relates to what you can do with nCode software. So as engineers, you're being asked to do things you haven't been asked before. For example, how are you going to take 35% of the weight out of the body and chassis of a vehicle? How are you going to reduce the total vehicle weight by, say, 400 kilograms? And, for example, can we justify making a cross member out of cast magnesium or perhaps even a composite material, while at the same time having to maintain the durability of the vehicle and minimizing the risk associated with these new materials, new suppliers, and new manufacturing processes? Now, these numbers I'm showing here are actually real weight savings from the current production Range Rover. But Jaguar Land Rover aren't the only company doing this, as we've seen in the 2014 Ford F-150 pickup. That uses a combination of a 90% aluminum body structure plus a high-strength steel frame, and that's achieved over 320 kilograms of weight saving. But there are many other manufacturers who are doing similar changes in order to move to lighter vehicles. So what's driving this global move to lighter vehicles? Let's take a quick look at what's the business driver for this. So really, in a word, it's regulations. The drive to reduce greenhouse gas emissions and improve fuel economy is being legislated in many regions around the world. Now, it's not always easy to compare those regional fuel economy standards, but if you look at it in terms of CO2 per kilometer and normalize that, and look at that, you see, like in this chart here, you see over the last 10, 15 years what those regulations have how they've changed, but also in the next 10 years or so, where they're going. Now, the major point from this slide is that these are not small changes. These are big changes. You look at the US there; it's reducing by almost halving the CO2 emissions. If you look over the scope of that time scale. So these are major changes to the fuel economy and the CO2 emissions from vehicles. And the equivalent number everyone's quoting to numbers that we actually can relate to. What the fuel economy figure that people are quoting here in the US is at 54.5 miles per gallon by 2025. Now, exactly what that relates to into the vehicles that are produced is not a trivial calculation in terms of what that really means. But whatever way you look at it, that's a major change in the corporate average fuel economy standard. So the takeaway here, major changes are required. So how are we going to do that? Well, we're not going to achieve major changes in fuel economy with only small changes to the vehicle. So we're going to have to do something more significant. And as we've already seen in vehicles that are on the road, new powertrains are part of the solution. So we're seeing increased usage of electric vehicles and hybrid vehicles, and that's going to continue to be the case together with a smaller turbocharged both gasoline and diesel engines. So absolutely, new powertrains are part of the solution. But lighter vehicles will also always help, and that's what we're talking about today, is the whole area of vehicle lightweightings. For example, a 10% reduction in the vehicle weight has been shown to produce about a 7% improvement in fuel economy. And also, if you're trying to improve the range of a battery, so if you're looking at electric vehicles, then a lighter vehicle is certainly going to help you. In fact, there's what people refer to as a virtuous circle of benefits when you make vehicles lighter. So if you remove weight from a vehicle, that means that for example, the suspension and braking loads are going to be reduced because of the vehicle weight. Well, that means you can then downsize those chassis components. And if you downsize them, you're going to save weight, which means you can then make something else smaller, and then for a given powertrain, for a given performance, you can then potentially use a smaller powertrain, have a smaller fuel tank, or a smaller battery, for example. So all those things can then those things can be reduced in size and so on. So that's a way in which reducing weight out of a vehicle has a knock-on effect that has a increasing benefit in terms of fuel economy. So lightweighting, although will not be able to achieve the reduced CO2 emissions by itself, is a major part of the solution. So that requires major changes to the vehicle to reduce that much mass out of the vehicle, and in particular to the body structure, because the body structure with its closures and glazing makes up about 40% of the typical vehicle mass. So that's a key place to start, is taking weight out of the vehicle body structure. Now, in the first instance, you can do that by looking at the changes to the materials used, and we'll look at that in a bit more detail in a few minutes. But it will also have impacts on the architecture in order to accommodate those new materials. So, for example, it's unlikely you can just take the steel parts and now just stamp those same parts out of aluminum and assume that you're going to get the benefit, because although aluminum is lighter, it's also less stiff. So you're going to need to increase section sizes or come up with different means of maintaining structural strength and stiffness by using manufacturing methods such as extrusions together with cast nodes, cast joints. So there are architecture changes that often go along with these new materials. And the change to use other powertrains for electric and hybrid also present challenges and opportunities for additional components in the vehicle and also accommodating those components in the vehicle layout. So those changes to different powertrains also have knock-on effects in terms of vehicle architecture. And the more change that's involved, obviously the more risk. So risk is involved in when you have to take a vehicle and make these major changes. Typically in the auto industry, even if a new model year looks significantly different to the previous model year, oftentimes the underlying components and architecture are pretty similar to the previous generation. So taking major changes in architecture has risk associated with it. Now, when we make those changes, though, what we need to ensure is, as part of the vehicle performance, that functional performance is maintained. Primary focus of today, we're talking about durability, and that's obviously key in order to maintain reduction in terms of warranty claims, but also to ensure that there are no failures of safety critical components and liability associated. So durability is a key requirement for functional performance. You also have to take into account with durability that the targets that you're using to sign off the design are still valid. If you're going to a different type of design or a different type of powertrain, then are you using the right design specs? Do you have the right vibration spectra for the component if you're using a different powertrain? Do you have the right loads to design this component if you're making major changes to the vehicle weight? So all these things also need to be considered as part of the target setting process for durability for a new lightweight vehicle program. Now, in addition to durability, as you know, you're going to have to also maintain the functional performance of crash and safety, stiffness, noise and vibration, and so on. So in order to do that, then from my perspective, as I look at that, that means we're going to need to do a greater, if anything, amount of computer-aided engineering in order to be able to assess these disciplines up front. So that means a greater amount of simulation in order to be able to assess designs. We're not going to get there by relying on doing more prototype testing. It's going to need more simulation up front. But it also is an increased opportunity for numerical optimization in order to provide input to that design process by varying geometry and shape and sheet thicknesses and even material variation to achieve the required performance goals. So there's an opportunity there, not just for simulation, but also for optimization to achieve these weight targets. And so that's going to require greater upfront simulations to understand these design trade-offs. And where there's a lack of technologies to enable these simulations, then the relevant parties must partner to create it. We're going to have to look at where are there gaps in what we can simulate and address those in order to be able to assess these performance trade-offs earlier in the vehicle program. So that's a brief summary of some of the issues around vehicle lightweighting, what's driving it, what the impact of it is. So let's now turn our attention to one of the key enablers and the challenges of material selection. We've talked about using different materials to save weight. So let's look at some of those trade-offs. And one of the main comparisons or trade-offs is that people look at is the trade-off between steel and aluminum and their potential for vehicle lightweighting. Now, there are vendors and industry groups who will happily give you the benefits of each. And perhaps as a good example, the Ford F-150, you see that there are justifiable applications for both. So that may well be where things tend to fall, as we'll see. But let's start with steel. And the use of high-strength steels has increased to over a fifth of the steel used in the auto industry today is high strength. But in order to achieve the 54.5 miles per gallon fuel economy target that we were just talking about, the US CAFE regulation, then there's the use of new advanced high-strength steels are going to be required. Now, these are high-strength steels that have a greater formability to enable more of the vehicle to be manufactured using high strength, but with thinner gauges. So that's the benefit of being able to use a high-strength steel, is being able to reduce the gauge and still maintain the required crash and durability, strength, performance. Now, in addition to the high-strength steel, you can also then use other techniques such as the use of laser welded blanks, which retain thickness only in the required areas. So you're only putting the steel with the right thickness in the area that you need it, and you can use thinner areas in other parts of the panel that aren't being used to carry structural loads. So in that way, you can also reduce overall weight. Now, studies have shown that the projected body structural weight savings by using advanced high-strength steels is around 25 to 30% for body structures. So that's a significant potential saving over today's existing construction methods. And one of the big benefits of high-strength steel is the relatively low material cost. It's a material people are familiar with. It has a low material cost. And because vehicle structures are typically already made out of steel, then the packaging implications are that you can carry over the same basic designs. And also a major benefit is that you can use your existing infrastructure both for production, so production, manufacturing, assembly lines, and also even downstream repair facilities. You know, the cost of repair, it's something that is already the way the vehicles are structured. So steel fits the way vehicles are already manufactured. So although the absolute weight-saving potential of high-strength steel may be less than other materials, the question is this enough saving? And industry groups would say yes, it's going to be sufficient even for the long term. But one additional point of caution for high-strength steels is that we also need to consider the impact of welding on strength. The high temperatures of welding tend to reduce the fatigue properties of high-strength steels. It's well documented that as you weld a steel, then the fatigue performance of that weld is fairly independent of the actual grade of steel that's used. Now, there are some post-weld treatments that can regain some of that strength, but in general, care will need to be taken to ensure that reduced gauge joints have sufficient strength. And simulation of these joints is therefore very important. So the knock-on effect of going to high-strength steels will be that, if anything, the simulation of welds and joining techniques of those welded structures will be very important. But overall, in summary, what high-strength steel and advanced high-strength steels will enable us to do is to optimize gauge thicknesses, reduce gauge thicknesses, and therefore save overall weight. So let's look at aluminum. So aluminum is already widely used in the auto industry for things like engine blocks and wheels, for example. And it has the potential in the application for body structures to provide a greater overall weight saving, up to around, it's estimated, 40% body structure weight savings. So that's quite significant. But the disadvantages are that there's an immediate material cost disadvantage for aluminum. And also, spot welding, for example, is more difficult for aluminum because of the increased conductivity. So now there are methods for doing that. There are methods on the market for being able to use spot welding with aluminum. But up to this point, manufacturers have tended to move to different joining techniques, such as the use of self-piercing rivets, or other methods, or using self-piercing rivets together with adhesive, for joining aluminum body structures together. And as we mentioned before, one of the disadvantages, or one of the impacts of using aluminum, is it requires some architectural changes, packaging changes to the vehicle to accommodate the required structure. We're already seeing aluminum having an increasing role, an immediate role in increasing usage in body and suspension components. So we're already seeing that taking place right now. But in terms of body structure design, the simulation of joints, so both the selection of the method of joining the body panels and also the upfront simulation of those joints to ensure the right number of joints in the right places is going to continue to be very important. Well, let's turn our attention to composites. There are many different types of composites, but let's look at three important categories, especially as used in automotive or are being looked at for use in automotive. Short fiber reinforced injection molding materials. These are often glass fiber filled, and they're already used in automotive applications, such as vehicle interiors, IP, instrument panels. That's one class. There's also long discontinuous fiber materials. So this would be examples such as sheet molding compound. These have been used for a while. They've been used as Class A surface body panels, and also other semi-structural components have been made with SMC. And thirdly, carbon fiber laminates. So the advantage of although the advantage of carbon fiber, there's a greater opportunity because of the strength of the material, and it's been used in aerospace for low volume applications. But the high cost of carbon fibers has prevented widespread use so far in the automotive industry. So the advantages of composites, we just mentioned carbon fiber, that has a great potential for weight saving. People estimate up to 60% weight saving of a body structure by using a carbon fiber approach. And also because of what you can do with a composite material, you've got the opportunity to have part consolidation. So what may take multiple stamped steel parts that you would weld together to form an assembly, there's perhaps the opportunity with a composite material to form that all in one go, and therefore you've got simplification of total assembly, reduction in total number of parts, and even the material itself then lends itself to new concepts of assembly, new concepts of design that wouldn't be possible in say, a stamped steel construction. So that's an advantage of a composite. As I mentioned, the disadvantage, especially of carbon fiber, is the cost. Currently, it is effectively prohibitive to use carbon fiber in any large scale. But I know that's something that is, there's efforts to see what can be done to reduce that cost. Another disadvantage is the production cycle times. If you're making a couple of 100,000 vehicles a year, then you need a sufficiently fast production cycle time, and the forming, curing of composite materials is a challenge to be overcome, to be able to get the appropriate production time. And in addition to the investment required, there's also the learning curve for engineers to move from metals to composites. So that's just a learning curve that engineers have to go up in terms of application, working with vendors, working with suppliers, finding the right type of material, seeing how that fits the application. There's a learning curve to move to a greater use of composites in the industry. But regardless of all those challenges, there's still increasing interest that we see in the use of more composites for structural applications. Because of the complexity of the material itself, though, simulating durability and failure modes of composites is a major challenge. So fatigue of composites is challenging because you've got multiple damage mechanisms, you've got failure of the fibers itself, you've got the cracking of the matrix, you've got things like delamination. So you've got multiple damage mechanisms, you've got failures initiating in different ways depending on the construction of the composite itself. Damage itself is perhaps more difficult to define than in a metal. You've got this diffuse and spread out nature of a failure, and the failure might be progressive. And the material itself is inhomogeneous, which means it has different properties in different locations, behaves differently in different parts of a part, and anisotropic, meaning that the properties of the material are different in different directions. And when it comes to durability, you've also the mechanical properties. You've got both temperature and environment sensitivity. So these provide major challenges to how to simulate how a composite is going to perform from a durability perspective. But it's an area in which nCode is investing a lot of effort and is partnering with automotive companies and customers such as yourselves to find practical solutions to help simulate fatigue earlier in the design process. Just as we're wrapping up looking at the different options for materials, we'll come back to simulation of composites and what we can do in our software in a few minutes. But what might be the most likely solution for weight reduction, as we're looking here at that challenge of selecting materials, the most likely solution is probably going to be a combination of different materials, including magnesium, where you are matching the mechanical requirements, the best mechanical properties where they're most needed. And an example of this combined approach, if you like, is the multi-material lightweight vehicle project that reduced the weight of a 2013 Ford Fusion by over 23%. And that was a joint project between the Department of Energy, Ford Motor Company, and VEMA International. And that's a great example where you were combining different materials of different types, aluminum, high-strength steels, for examples, and even composite materials in certain components. And one of the challenges, though, as we mentioned before, of joining multiple materials together is then what mechanism do you use for join those? And in this particular project, they primarily used self-piercing rivets with adhesive to join the different components of the structure together. So that's an interesting example. So that's outlined some of the challenges of material selection. Let's look now at how nCode software can help you, how it can help reduce the risk of these changes with regards to durability performance. And the nCode product used for upfront design evaluation for durability is nCode Design Life. And Design Life enables you to predict fatigue from finite element simulations, and it supports a range of well-proven methods such as stress life and strain life calculations. It works with the FE codes you already use and has many advanced capabilities, including the fatigue of spot welds, seam welds, and composites, plus others, but those are the ones perhaps we're going to focus most on today, as part of the standard product. An important part of vehicle lightweighting is numerical optimization. And in order to do that, you then need to be able to run software in batch. And nCode Design Life is fully batchable. So optimization, as we saw earlier, is going to be one part of vehicle lightweighting. How do you say reduce gauge thicknesses? How do you change shape in order to reduce weight and still maintain stiffness and strength? And so nCode Design Life is fully batchable, and we already have customers using it with a wide range of the industry tools that are out there, Mode Frontier, Tosca, EyeSight, for example, to assess durability as part of a multidisciplinary design optimization process. And as we mentioned, the optimization there would be for optimizing, say, gauges and shape for maintaining durability. So as part of optimization, though, that means typically running a large number of different analyses. So this requires a fast turnaround of results in order for the optimization process to be practical. Now, one way Design Life enables fast runtime is by supporting parallel processing, and it does that on a single machine. It also supports parallel processing in HPC environments. So, and in fact, near linear scaling is achieved by doing so. Increasing the number of threads or spreading over more compute nodes, you can get almost linear scaling to reduce the computational time required. And we do that through the use of industry standard MPI running on Microsoft HPC or other cluster environments. So takeaway there is, if you need to go faster, you can. Design Life is fully batchable and will take advantage of these computing facilities, including HPC environments, in order to be able to use that as part of an optimization process. As mentioned earlier, the fatigue of composites is particularly challenging. Design Life enables an assessment of the durability of fatigue of short fiber composites using an SN approach, using a stress life approach. An example would be using for glass fiber field thermoplastics. So in this case, we read the stress results from the finite element analysis, and we can read that for different layers, composite elements that are used for the model. And we also combine that with results from a manufacturing simulation. The manufacturing simulation for the composite will then provide the orientation and of the fibers in the material. So it gives you the degree gives you the orientation of the fibers, but also gives you the degree of how aligned they are. What's the distribution of fibers, and we describe that as being the fiber share. Now, in design life, we've actually got two material models for doing that. We can either do that using multiple SN curves based on the fiber share. So it interpolates that depending on what the fiber state is at that location. Or alternatively, you can link it with Digimat software from Extreme Engineering and use Digimat to calculate the SN curve at each location using its own method for that material model. So we can do that two different ways. So that's part of a design life in its standard product. Now, what's coming in version 11, which will be the first quarter of next year, is something that helps, which is actually using an energy method approach for composites, because that use of fiber orientation adds some complexity to the process. And by using a strain energy approach, you can actually help reduce that complexity in the calculation. So this method that's coming with regards to strain energy approach, which is calculated from the product of both stress and strain at each location in the model, that method adjusts for mean stress, and it uses a power law relation that simplifies the materials data requirements by simply representing the relationship between this energy-based damage parameter and the number of cycles to failure on a single curve. So this is a new method that's coming in the new year, and there'll be more details on that when we release it early in 2015. Another capability of design life is the assessment of adhesive bonds. As we've seen, this is important for joining of aluminum and dissimilar materials. And the software uses a fracture mechanics-based method to assess the critical joints. Now, the modeling method of the adhesive is actually quite simple. It uses beams to recover forces where the adhesive joint is, and then the result is a safety factor shown on the flange of the joint. And this method is also described in the SAE paper that's shown there, if you want to look at the details of what's behind that. So we have a methodology to be able to calculate a safety factor to assess where there may be durability concerns for adhesive joints, adhesive bonds. Now, as a real-world example of using design life in vehicle lightweighting, Jaguar Land Rover have been investigating methods of simulating the fatigue of self-piercing rivets in aluminum body structures. They decided to adapt the existing method of predicting the fatigue of spot welds that was in the software and use that to see if they could replicate the failure modes of rivets. So in order to investigate this, they performed a range of coupon fatigue tests for both simple lap shear joints and also coach peel test specimens. And they were tested for a combination of different sheet thicknesses and also load amplitudes. So they used that and they then simulated those test specimens using what was meant to be a spot weld model, but they were using it to see how well it correlated. Now, not surprisingly, when they did that, the initial calculations for using a spot weld model for these test cases didn't give good correlation to the fatigue of the riveted joints. The equation shown there indicates the relationship used in the software to convert the forces calculated in the spot weld elements in the finite element model to a structural stress in the sheets. So this is a standard part of the software to enable the relationship between the diameter and the thickness of the joint and the resulting structural stress to be defined. So in this case, what Jaguar Land Rover did was they used numerical optimization to adjust these numerical parameters to get a better fatigue prediction of the riveted joint. So by optimizing the model parameters, they were able to get a much better outcome. And the result was then a useful model for predicting top and bottom sheet failures that matched well with when applied to a large number of other known test results. And so each pink dot on this chart is a test result, and the green dots in a line is being the CAE predictions. So together, this then enabled the full body in white of this aluminum structure, together with self-piercing rivets and adhesives, to be modeled for durability assessment using design life, using real vehicle loads, and also enabling all the visualization of those results, the failure at joints, the individual rivets to be visualized to assess the durability. So that gives one example of an application, but we work with many other companies as a technology partner for durability. And as part of the organization within the nCode brand, we have a technology group, and we have a major focus on composites as a primary focus for ongoing research. And if you have interest in that area, we would be happy to discuss what your industry application is and see how what we're doing meets your needs and what your current interest is in composites. And we also have, as a company, an advanced materials characterization and testing facility in the UK. So this provides validation for our own technology validation for our own technology developments. So it's a testing facility we use to validate the methods. And also we have opportunity there for running external customer projects as well at the testing lab in the UK. And an important part of our approach is that we see that it's important for us to partner with as many CAE companies as possible to maximize the interoperability and to be as solver neutral as far as possible, so that our tools fit within your engineering process, regardless of the CAE tools that you've chosen to use within your environment. And finally, it's perhaps encouraging to know that 16 of the top 20 OEMs, automotive OEMs, use nCode software. 8 of the top 10 global suppliers, and 73% of the top 40 global auto suppliers also use nCode software. So to conclude, vehicle lightweighting is needed, material selection is challenging, and nCode can help you, as we've seen, to enable durability to be included in weight optimization, to assess the strength of welds and other joining techniques and new joining techniques that are being required, and also to develop new methods for assessing the fatigue of composites and other new materials. So that's given you hopefully a summary of where we see our role in assisting with these vehicle lightweighting programs, what aspects we're doing, what we're doing to help to enable that. And so thank you for joining us today. I also like to also just acknowledge, as part of that bonded car work we were describing with adhesives and self-piercing rivets, that was a collaborative research project that was co-funded by the UK's Technology Strategy Board. So I just wanted to acknowledge that as well.